All right, today is a special little vignette. This is an extra example of a proof of correctness for loops, proving loops correct. And the last time we did the multiplication algorithm, this time we're going to do the division algorithm. So here is a description of the algorithm. We have precondition. It's 12.46 in the book. We have the precondition Q is B is greater than or equal to 0 and C is strictly greater than 0. And then we have this Q and R. Now Q and R, Q stands for quotient and R stands for remainder. Okay, so, and we assume that, that B and C are given. And let's jump down to the postcondition. The postcondition R says B equals Q times C plus R, and 0 is less than or equal to R is less than C. So C is the number that we're dividing by. Maybe I can do an example here. Okay, so for example, if B is 17 and C is 5, then what we're doing is we're dividing 17 by 5, right? So 17 divided by 5, so here what we're saying is that 17 divided by 5 equals what? Equals 3, right? Because 5 goes in 17 3 times with remainder 2 equals 3 remainder 2. Okay, so this 3 is the quotient. So this 3 is the Q. Q stands for quotient, and this 2 is the remainder R. Okay, so the problem is to calculate Q and R given B and C. Does everybody see that? So look at what the postcondition says. The postcondition says B equals Q times C plus R. So here it's B equals Q times C plus R. So in this particular example, 17 equals 3 times 5 plus the remainder is 2. And notice that this, we want the remainder to be greater than or equal to 0, but strictly less than C. This remainder has to be strictly less than 5, right? So this is an example of what the division algorithm would compute. So this would be given. This is given, and this Q and R is what's computed. Then it's computed, and so what we want the postcondition to be is we want the postcondition to satisfy that condition. B equals Q times C plus R. All right? Are you with me? Is everybody with me? Okay. All right. So, so here let's take a look at at our little checklist before we go on. So remember, we have 4 things on our checklist. So our checklist in P.30 is a proof method for do. It's the same as 12.45 in the book. First of all, we have to prove the initialization is correct. So we have to do Q initialization P, so that's A. And then for part B, we have to show that P is a loop invariant. So remember this, B is P and B. Now remember, what was B? Remember what B was? Right, B is the guard. Okay, so B is the guard, and then and then S is a statement inside the do loop just by itself, right? It's the statement part of the guarded command, right? And then P is the invariant. Okay. And then C, part C, we do have to have an argument for why the loop terminates. And then we do that a little informally. And then for part D, R holds upon termination. So we have to prove that R holds on termination. So we do P and not B implies R. Now why would not B be true at the end? Yeah, because if B is true, the loop will go again. So the only way that we break out of the loop is if the guard is false. right? So we have to prove that the invariant and the negation of the guard implies the postcondition. Right? Are we good? Okay, so here we go. Let's show this back again. Okay. So this is 12.46. 12.46 in the book, division algorithm, proof of correctness. So we're not deriving this time, we're proving correctness. Okay, so A, we have to do the initialization. So what does it say up here in 12.46? We've got Q, and there's our precondition. We've got the initialization statement is Q comma R gets 0 comma B. And then we have a semicolon to separate that statement from the do statement, right? So for part A, we have to prove, and here we'll just use the letter Q for that abbreviation. So Q implies WP, the weakest precondition, dot, and then the statement here, the initialization statement is Q comma R gets 0 comma B, dot, and then the invariant P, we'll just use our P for the abbreviation there. Yeah? Is that good? Well, now, how do we do this? Right. Assume the conjuncts of the antecedent. Okay, so Q's the antecedent, so we'll assume that. So we'll start with this, we'll prove that this is true, and we can use either one of those conjuncts whenever we want. Okay, so we start with WP dot Q comma R gets 0 comma B dot P, and this equals by our old friend, right? P.18 and textual substitution. So what do we have to do? We have to substitute in, let's see, how does that work? We have to substitute in, everywhere there's a Q, we make it 0. Everywhere there's an R, we make it B into P. So what does that give us? B equals what?
0
times C plus B. And
0
is less than or equal to B. Okay? So this equals by, oh, well, this one's easy, right?
Yeah.
I mean, 0 times, so we do a little math here. So math, and yeah, so 0 times C is 0, so B equals B. We know B equals B by math, that's true. And then true and this. True is the, what, identity for and?
Yeah.
Math and identity of and, identity of conjunction. So that's going to give us 0 is less than or equal to B. Where do we go from here? What technique are we using? Assuming the conjuncts of the antecedent. Well, let's take a look at one of those antecedents, one of those conjuncts. Which conjunct looks like a good one there?
B is greater than or equal to
Yeah, assume conjunct B is greater than or equal to 0. So this is true. Boom, got part A. Are we good? Okay, let's go over here, do part B. So, by the way, you notice that how this works is, if you look at this at the body of this do statement, it subtracts. It takes R gets. I'm sorry. Yeah, Q gets Q plus 1. So R is initialized to B, and it successively subtracts R from R. And then it counts how many times it subtracts. So in the same way that the multiplication algorithm worked by adding and counting how many times it added, or it didn't count, but it added the number of times of the other one. So this is successive subtraction. Okay, so. All right, so what was B? What do we have to prove for B? We had to prove that, now this time when this statement executes, the guard is true, right? So what we have to do in step B is to prove, what was it? P, how did that work? Do you see it on your?
No.
Okay, so okay, so P, you don't see it. Okay, so P and B implies the weakest precondition dot, and now here's the statement. So it's Q comma R gets Q plus 1 comma R minus C dot, and here again we'll just use the abbreviation P. And as always, we'll use a technique of assuming the contents of the antecedent and do this. Okay, so we have WP dot Q comma R gets Q plus 1 comma R minus C dot P equals by 3.18. Oh, P.18, yeah. P.18 and textual substitution. None. Now, we got to go look at our P, right, which is this one now. And everywhere there is a Q, put a Q plus 1. And everywhere there's an R, put a what? R minus C. So what will that be?
We're putting the variant.
Yeah, P right here. We're doing this textual substitution into this. I mean, we're doing weakest precondition. So everywhere there's a Q, replace it with Q plus 1. Everywhere there's an R, replace it with R minus C, and into the invariant, right?
Okay.
Q plus 1 times C, and in parentheses there, right?
Yeah. Plus R minus C.
Plus R minus C.
Oh.
But there's more, right, to the P.
And
And-
is less than or equal to R minus C.
All right, is everybody good? Okay. So let's do a little math. Now, oh yeah, here we have a Q plus 1. So this is a Q times C plus R minus C, so the C's cancel. So what will we be left with here? B equals what?
B equals Q times C plus R.
C plus R. And we can just take this C to the other side, right? And let's call this R is greater than or equal to C, right? Oh, what technique are we using here? We're probably going to assume some conjuncts. Yeah, it's P and B. So, oh, which conjunct can we get from the P?
B equals Q times
C plus R. Okay, so this equals, assume conjunct, B equals Q times C plus R. Oh, how convenient. That's exactly that one. But now what about this one?
Well, that looks like the guard.
This,
Conjunct.
the guard is P and B. So the guard is what? Oh, so R is greater than, so here's the guard, right? This one's the guard. This is the B, yeah? So,
That looks familiar.
oh, it does, son of a gun. It just happens to be that. So we have true and true, which is true, right? Equals, blah, 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 true. Boom. Are we good? Now, what's the third thing we have to prove? That the loop does what? Terminates. Ooh, how are we going to prove this? Do you think this loop will terminate? So here, C.
Strong feeling.
You have a strong feeling it does. Prove. I have a very cooperative cameraman here. Prove the loop terminates. Okay. In order for it to terminate, what has to happen?
C has to be greater than R.
C has to be greater than R.
And since you subtract C from R,
And each time you go through the loop,
and C is guaranteed to be greater than 0, so R is decreasing each cycle no matter what, which means eventually it'll be less than C.
yes. Okay, did you guys hear that? So regardless of the initial value of R, let me write that out. Regardless of the initial value of little r, of r, each time through the loop it decreases by c, right? Each time through the loop, it decreases by c. It decreases by c. And what is the value of c? C is, yeah, c is positive by the precondition, right? And c is positive by q, comma, and c is positive oh, by the way, does c ever change? Does the loop ever change the value of c? No. And c is positive, parentheses, and unchanging. By the precondition, by q. All right, by the precondition of the whole loop. And the guard is, but what is the guard? The guard is r greater than or equal to c. So it will eventually be false, and the loop will terminate. So it will eventually be false. And the loop will terminate. So that's our proof of termination. And now we have only one more thing to do, and that is step D. Now, what was step D? Step D was the thing at the end, right?
P and not P implies R.
Yes. Because when we end the loop, the guard has to be false. That's how you end the loop. So once we end the loop, we know the guard is going to be false. We know that the P is invariant. Okay, so because we proved that P was invariant, right? And then, so what we have to do in D is to prove P and not B, not the guard, implies R, which is the postcondition of the whole computation. Now, the way we're going to do this now is we're going to start with R, and we're going to assume the conjuncts of the antecedent, obviously. But this time we're not doing a WP calculation, right? So we'll just start with R. Okay, so assume conjuncts starting with R. Prove R assuming conjuncts. So we'll prove R true assuming conjuncts. Conjuncts of antecedent. Okay, so let's write out R. What was R? It's all of that, yeah? So can you read that off for me? Well, what's an easy one right away?
You can assume P, or assume B equals
Q times C plus R. That's one of the conjuncts right away. Okay, so that's the easy one. Assume conjunct B equals Q times C plus R. So then I won't bother to write out. And the identity of conjunction is true. It's true, and this is this, right? So this is 0 is less than or equal to R is less than C. Now, how do we handle something like this, though?
well,
What does this actually mean? This
0
is less than or equal to R,
and
and R is less than C. So that's conjunctive meaning, right? Conjunctive meaning of these inequalities is 0 is less than or equal to R, and R is less than C. That's the conjunctive meaning. Now, what is Now what? Now that we've written it like this,
We can assume P again.
yeah, we can assume P and, so which conjunct, I mean, there's a conjunct right away, isn't there?
Yeah, that's that one.
It-
Zero is less
Isn't it 0 less than or equal to R?
is true.
Yeah, because that's one of the conjuncts right directly in P. So here, let's do that one first. So this one equals assume conjunct. Uh, 0 less than or equal to R. And so true and this. So we have R is less than C. But now what?
Well, you can assume not P.
Yeah, we assume conjunct. Yeah, so this equals by we assume conjunct not, now what was B, the guard?
Yeah, R.
Not, R is greater than, not, R is greater than or equal to C, which is what?
R is less than C.
Uh-huh, so that's true. Boom, and we're done. So put that in your pipe and smoke it.